So we've looked at inverse functions as a set of ordered pairs. We've looked at inverse functions from graphing, and now it's time to find the inverse function given an equation. We're going to use these steps again when we look at exponential functions and logarithmic functions. So make sure you feel comfortable with the steps so that we can use them again without spending a lot of time reviewing them. So the first thing we want to do is change f of x to y. And now remember, in inverse functions, x and y switch places. It's as easy as that. So all of the x's become y and y becomes x. Here's the hard part. We have to solve for y. That means we want our equation to say y equals. Well, the first thing I notice is I have y in the denominator and I don't want it in the denominator. So let's get it out of there. I can open the brackets on the left. We're still solving for y. That means we want all of our terms with y on one side and our terms without y on the other side. So I've subtracted 2y and I've added x. Now we have all of our terms with y on one side and we see that y is common. So we can factor. We divide both sides by that x minus 2, and we see that y equals 1 plus x all over x minus 2. Our final step then is to change y to the inverse function, because now x and y have switched places. We have found our inverse function. A final step is to verify. We need to show that f composed with the inverse equals x and that the inverse composed with the function equals x. Verifying is great algebra practice, especially when we have these rational functions that we have to verify. So remember, there are two steps here. We want to find f composed with the inverse of f. It has to equal x. And the inverse composed with f has to equal x. Now, what I see pretty often on tests and exams is people don't have the correct inverse function, but they know it's supposed to equal x. So when they're verifying, it magically does. I would rather you said to me, wow, this doesn't equal x, and I know it should, but I can't find my mistake. That shows you understand what's going on. Mistakes happen, and if you can't find it in the time allowed during a test or exam, that's fine. Don't pretend it's all okay when it's not. So why don't you do the first step there, f composed with the inverse function. I wanted to show you this substituting first of all, and I used a different colored pen so you could see the inverse function. I had to change each x to f inverse. Now we have a complex rational expression that I hope you can simplify. We bracketed the numerator and the denominator, wrote this as a horizontal division question, and I'm multiplying my terms by the missing factor, so each bracket is over a common denominator. So we simplified, we found that x minus 2 is common, 3 is common, and it equals x. Great. Now we have to do the other verifying. we have to compose the inverse function with f. Pause your video, give that a try. So again, your substitution was a little bit tricky, but I put that in green here for you to see it. We wrote this as a horizontal division question and then over a common denominator. We found that x minus 1 is common. And then 3 is common. It equals x. So we did this whole question correctly. We did find inverse functions. Before we end this lecture, let's find the domain and range of our function f of x equals 2x plus 1 over x minus 1. The domain should be easy. We've done that before. We know the denominator cannot equal 0, and so we know that x cannot equal 1. But I've never asked you to find the range before. Remember what we said about the range. It equals the domain of the inverse function. We found the inverse function for 2x plus 1 over x minus 1. Here's our inverse function. So to find the range, we just need to find the domain of our inverse function. We see that x minus 2 cannot equal 0. Therefore, y cannot equal 2 in the function. So using interval notation, we'll do some more practice in the next lecture.